Okay, ladies and gentlemen, so today we're going to talk about lesson 6.3, which is solving systems of equations by simple elimination. We'll make it a little more complicated when we get to 6.4 and we'll use full elimination, but today we're going to focus on simple elimination. So we're still working on the same skill as before. We're solving systems of linear equations exactly and approximately, focusing on pairs of equations with two variables. Our first and only vocab term for today is the idea of elimination. Elimination is a method of finding an exact solution to a system of linear equations. It's most useful when both equations are in standard form. So like I talked about when we were doing the last lesson here, if we have two equations in standard form, there may be a better way to solve it, and that would be using elimination. However, using what you know, you can rewrite any equation into a different form so that you can solve it the way that you are most comfortable with. The ones that are set up like this will be easier to solve in elimination, but if you decide that you hate elimination, you can rewrite it to isolate a variable and solve by substitution. Same the other way as well. If a variable is isolated, but you decide that you like elimination best, you can shuffle your equation around algebraically so that you have the form that you're most comfortable with. So in your notes, I want you to write down the 3 steps to solve by elimination. Pause the video now if you need to. You're going to write the system so like terms with the same or opposite coefficients are aligned. What I would like to do is I like addition best, so I want to make sure that I have opposite coefficients, and we'll talk about how we can rearrange our equations so we have our vertical alignment there. The next step, we're going to add or subtract if you didn't have opposite coefficients to eliminate one variable and solve for the other one. Then you'll take that in step 3, you'll take your solution from step 2 and plug it back into one of the original equations to solve for the other variable, and you'll write your solution as an ordered pair. So let's practice with this. With this system here, I see 2 equations in standard form, that ax plus by equals c, and I see that it's already set up. I have opposite coefficients on y. My b value in the first equation is a positive 1, and in my second equation it's a negative 1. So what I'm going to do here is I'm going to set up a giant addition equation. When I have the system copied, what I'm going to do is just going to write it out like a giant addition equation. Now the reason this works is because what we're really doing when we set up this giant addition equation is I have my first equation, 3x plus y equals 4, and I'm adding the same thing to both sides. On this side of the equation, I'm adding 2x minus y. So I could add 2x minus y on the other side, but that doesn't help me. That doesn't get rid of variables. I know that 2x minus y is equal to 6. So I'm adding the same thing to both sides of the equation, but I'm making my life easier by solving it vertically instead of rewriting it out as a horizontal equation. All right, so back to the original problem. When I do this, I get 3x plus 2x gives me 5x, and my y's are eliminated. Just like I had 3x plus 2x and a plus y and a minus y. Then on my other side of the equation, I'm left with just those constants, 4 plus 6. So I get 5x equals 10. Well, to get x all by itself, I need to divide both sides by 5, and I get a final answer of x equals 2. Much faster way of getting to one of our variables solved than by using our other methods. But I could have, if I took that original equation, let's erase this off now. If I took that original equation, come on, keep erasing, there we go. I could have subtracted 3x from both sides and wound up with a new equation that looked like y equals a minus 3x plus 4, and then substitute it in. Any way works. As long as you are doing mathematically legal steps, you can solve this in multiple ways. So going back to this idea of elimination, I've solved for my first variable. Now I need to go back and plug that into one of my original equations to solve for the other piece. I'm going to use the first one so that I don't have any negatives to get me confused. And I get 3 times my value for x plus y equals 4. Well, I just found out that x is 2. So when I plug that in, I'm going to use my equation solving skills. I know I need to multiply. I get 6 plus y equals 4. If I take away 6 from both sides, I get a y value of negative 2. So my final answer for this system is going to be my x value first and my y value second as an ordered pair. Well, let's try again. If I look at this system here and I set up my giant addition equation, nothing cancels out. I have a 3x and a 3x, but they're both positive. So what I need to do is really create a giant subtraction equation. I'm going to subtract everything from it. When I'm subtracting, I need to remember that I need to subtract each piece. So I have 3x, and I'm going to take away 3x. Well, that's going to go away. I have 4y. I need to take away a negative 2y. Well, minus a negative is really the same thing as addition, so I get 6y. And 2 minus 8 gives me a negative 6. Now, if this step confuses you, what we can do is we can really multiply that second equation by a negative 1. If I rewrite it, so I'm multiplying 3x minus 2y equals 8, all by a negative 1, that second equation turns into a negative 3x plus 2y minus 8, or equals a negative 8. If I restack my equations, I'm going to rewrite the first equation again, that 3x plus 4y equals 2. Well, then I have it set up for my giant addition equation. If you're getting lost with your negative signs, I suggest that you rewrite it this way so that you know what's canceling out and what isn't. If I look at this here, I get my 3x and a minus 3x, 4y plus 2y, and 2 minus 8. I get the same answer as I do here, so whichever way works best for you. Then my next step, I have to divide by 6, and so I find out that y is equal to negative 1. Well, now I'm going to go back. I'm going to erase this stuff out of the way here. Oh, there's got to be a better way. All right, we're going to leave it alone because I can't erase. We're going to plug this back into that first equation. So I see that I have 3x plus 4 times my y value equals 2. Well, my y value is negative 1. That leaves me with 3x minus 4 is equal to 2. If I add 4 to both sides, I get 3x equals 6, which tells me that x equals 2. Last step here, I'm going to write it out as an ordered pair. Even though I solved for y first, my ordered pair is always going to list my x value first and my y value second. So I find out that the solution to this system is 2, negative 1. Now, when I'm talking about these systems here, just like before, I can have one solution where I get a value that looks like this. I can have infinitely many solutions where if I'm adding stuff up and I get a statement that's true no matter what, like 7 equals 7, that would tell me that there are infinitely many answers. If I wind up with a false statement, if somehow both my variables cancel out and I get something like 2 equals 4, that tells me that there is no solution to the system. So one more practice problem. This one's out of the homework. I think it's number 32. We need to let x represent the number of years since 2004 and y represent the number of catalogs. So we're trying to figure out the number of catalogs that were sold or distributed per year since 2004. If I look at this here, before I write the system, I want to just analyze the numbers. I see that in 2004, online had 7,440, and then a growth rate that's positive. In 2004, the print catalogs were 3,805 with a negative growth. So that tells me that they are decreasing each year. So when I look at this information, I see that I really have a start value and a rate, or a rate of change. So that tells me my equations are going to be in slope-intercept form. That the number of catalogs is equal to the starting value plus the rate of change times x, the number of years. For my other equation, same thing. I have the number of catalogs is equal to that starting value plus, or in this case, minus that change per year. The textbook says to use elimination. Well, I'm telling you that this one here is set up to go with substitution, not elimination. So I'm going to tell you, you can use your judgment here, and instead of solving it by elimination, we're going to solve it using special substitution. Now, normally when I see two equations in slope-intercept form, I might think that graphing is the right choice. But if I look at those numbers, they're really big. So graphing would be a challenge. Not impossible, but it would be a challenge to do by hand. So what I'm going to do is this idea of special substitution. Because I see all of this stuff is equal to y, and all of that stuff is equal to y, I can set those two pieces equal to each other. That expression from the first one, 7440 minus 1293x, is going to equal the second part, 3805 minus 1364x. That special substitution tells me I can set them equal to each other. And now I just need to use my equation solving skills. So if I add 1293x to both sides, I get, where did I get my answer here? Oh, I'm going to add 1364x to both sides, just because that's what I have on my note paper here. And I get 2657x oops, that was a plus. That's where my mistake is. That plus here, I almost copied my problem wrong. When I do that, I'm left with 3805. Well, now if I subtract 7,440 from both sides, I get 2657x is equal to negative 3,635. Dividing both sides by that 2,657, I get x is equal to negative 1.368. Well, now I need to go back and find the y value. So if I do that, I plug in this negative 1.3678 into that first equation, and I'm running out of space here, so show your work on your page. When I plug it in, I get 7440 plus 1293 times negative 1.368, and that simplifies out to a y value of 567.176. 567.176. Well, now let's think about it. We'll think about the reasonableness, this last part here. That solution tells me that x is negative 1.368. Well, x represents the number of years since 2004. So the fact that it's a negative number tells me that this happened 1.368 years before 2004. Which is possible. Lots of times we have negative numbers are not reasonable solutions, but in this case here, it tells us that it happened before 2004, and that y value tells us the number of catalogs. Well, I can't have 0.176 catalogs, so I really should round this to the nearest integer value. So y is really 5,671 catalogs. So that this solution tells us that 1.368 years before 2004, online and print both had exactly this many catalogs. When we're determining reasonableness, this is where you have a little bit of freedom. As long as you can justify your solution, whether it's reasonable or not, I would accept either answer. But in this case, I would say that it is a reasonable solution. We would expect that online and print catalogs were the same amount in some year, and so happening before 2004 makes sense. One way that you could argue that this is not reasonable is because we get a decimal value and we can't have a portion of a catalog. The other way that you could argue that it's not reasonable is that we could predict that that growth rate might not be constant. And we have it listed as a constant growth rate, so we are expecting it to be a linear equation. But if we're using our knowledge of the real world, it may be more reasonable to expect that that growth rate is not constant. Different ways that you can argue this here. Make sure that you have your work written down. And let's get started on some homework. Your homework is from page 353, numbers 3 through 30, multiples of 3, number 32, which is the one that we just solved together, and then 34 and 35. When you're done, make sure you check the files section for the key and self-grade your work so I know we're ready to move on.